So I'm just playing with a high school mathematics. Cubic functions. Okay, cool. So basically, what are cubic functions? These are functions that have an x raised to the power of 3 cubed. X cubed. That's why they're called cubic functions. So you literally have your f at x. You literally have your f at x being equals to a x cubed plus bx squared plus cx plus d. This is a cubic function, right? How do you know this is a cubic function? Because x is raised to the power of 3. This is a cubic function, right? And what is a quadratic function? We touched on quadratic function. Let's just say q of x. It should be ax squared plus bx plus c. This is a parabola or a quadratic function. This is a quadratic function. Then you have another type of function which is a linear function. Let's say L of x. That literally says you have your mx plus c, right? That's your linear function. But today's lesson is mostly focusing on cubic functions. What are cubic functions? Okay, cool. Okay, cool. So we literally said your cubic function, it literally, let's revert to 100% zooming extent. So you literally have your f at x being equals ax cubed plus bx plus cx plus a d. The logic is still the same for your x-intercept. So let's start by divulging into the shape of the function. How does it look? How does the cubic function look? Generally, you have your xy plane, right? This is your x and this is your y. Your cubic function can look like this, or your cubic function can look like this, depending on some parameters. Under which circumstances does your cubic function start by going up, then going down, and then going up again? So when your a is greater than 0. Okay. This is when your a is greater than 0, and this is when what? This is when your what? This is when your a is less than 0. What is your a? This coefficient of what? Of x cubed. So if it's greater than 0, you should expect something like this, You expect something like this, You expect something like this, right? But if it's less than 0, you expect something like this, So that's the simple logic, right? So I think you're realizing that your cubic function also does have the x-intercepts. It has the x-intercept, and it also has one y-intercept. You get what I'm saying? It also has one y-intercept. Okay, cool. How do you determine the x-intercepts and the y-intercepts of a cubic function? It's simple. The logic is still the same. For your x-intercept, you let your y be 0. For your y-intercept, you let your x be 0. Okay, so you literally say, for your let's start with the y-intercept. For your y-intercept, you do what? You let your x be equal to 0. So that means you literally have your f at 0. You remember you had ax cubed plus bx squared plus cx plus d. So you literally have now a into 0 cubed plus b into 0 plus squared plus c into 0 plus d. You know that if you're multiplying anything with 0, that thing goes away, it falls away, it becomes what? It becomes 0. So that means your f at 0 then becomes then becomes d. So that means in your cubic function, the coordinate of the y-intercept is 0 is to d, right? Because you let x be 0 and you got a d when you plugged in x as 0, right? That's always the case in a cubic function. Okay. Let's go to the x-intercept. This is a bit interesting. Okay, now the x-intercept, how do you determine the x-intercept? If you want to find the x-intercept, it's simple. You let your what? You let your y be equal to 0. So you literally have, for your x-intercept, you do what? You let your y be equal to 0. So you literally have f at x, you equate it to what? To 0. Your f at x is 0 because your f at x is more like a y. So that means you literally have your ax cubed plus bx squared plus cx plus d all equal to 0. That's how you determine your x-intercept. One might be wondering, how do you then solve for x under these complex, like this is so complicated, you can't even open factors, you can't even open, there's a cube. Do you remember we used to open factors when there's a squared? We just solve for x if there's like a linear function. But now we have a cubed. How do you do it? There are multiple ways of doing this, but the more logical way of doing this thing, some people, they do it using long division. I don't prefer that. I prefer using logic when I am solving this. So we'll have to wait until we do an example so that it becomes simpler, right? Okay, cool. So let's move on to the next phase of this function. We'll do an example and everything will become clearer as we do an example. Okay. Let's go to, how do you then determine the turning point? You remember we did derivatives. So you should always know that a derivative of a function gives you a gradient of that function, right? So if you derive a function, you're determining a gradient of that function. So what am I implying? You remember when you derive a quadratic function, you get a linear function, right? When you derive a quadratic function, you get a linear function. That means a linear function is a derivative of what? Of the quadratic function. So that means a linear function gives you a gradient of a quadratic function. Same applies with a cubic function. If you derive a cubic function, you get a quadratic function. That quadratic function gives you a gradient of that cubic function. What am I implying? Okay, let's skip this now. So it's literally here we have f at x equals ax cubed plus bx squared plus cx plus d, right? So if you take a derivative of this, you literally have 3ax squared plus 2bx plus c, because the derivative of a constant is 0, like it falls away. So what does this now imply? So let's say they asked you to determine the gradient of this function, the cubic function, at the point where x is equal to 1. So what are you going to do? You're going to take a derivative of this function, then plug in x as 1 here. You plug in x as 1. You plug in x as 1 here, right? Because when you derive a cubic function, you get what? You get a gradient, or you get a quadratic function which describes the gradient of that function. Where am I going with this? You remember the function, the shape of our function is like this. The cubic function literally has this shape, né? You must know that at the turning point, the gradient is 0, né? The gradient is what? The gradient is 0, because if you draw a line here, it literally becomes straight, né? It's a straight line here. Even here, there is a straight line, right? So a gradient is more like a tangent at that point. You get what I'm saying? So that means our gradient is 0. What does that imply? If you wanted to determine the coordinates of the turning point, you literally say the coordinates of the turning point is when your gradient is 0. So that means you take this whole equation over here. You take this equation. You remember the equation that we just developed, this one, né? You just take this equation. Okay, you take this equation. Let's go here. Let me delete this. Okay, so you take this equation. You remember this was your f prime of x, right? This was literally your first derivative, right? This is your first derivative. And you equate this to 0. You remember now you can literally solve this easily because you have a squared. So you can literally open the bracket and solve for x values. After determining the x values here, you should always substitute the x values back to the original function, because you'll be plotting to determine the coordinates at this point, but you were using the logic that at the turning point the gradient is 0, that you use that to determine the x values. And to get the y values, you should always substitute them back to the original function, not to the derivative, right? Because if you substitute them back to the derivative, you'll get a 0, because at those x values, the gradient is 0. You get what I'm saying? It'll be more like you're just calculating a gradient. So to get the y value, you substitute back into the original equation. And also, you should note something about this function. Let me redraw it again. When you look at this function, it starts by going up, and it goes down. It reaches a point where it changes the concavity. So it literally changes from, you see it's concaving down, right? It's literally concaving downwards, It's concaving downwards, But from this point, it starts to change the concavity. It concaves up, It concaves what? It concaves up. So there is that point where there is like an inflection. Hence, this point is called point of inflection. You see, it was going down. Now it's starting to go up. You know what I'm saying? It's starting to go up. It's going up. And it changed the sign at this point. And this point is called what? The point of inflection. Point of inflection. This is a point of inflection, right? Okay. So how do you determine the coordinates of the point of inflection? You literally take the second derivative and equate it to 0. These things will become more clearer once we do problems, we do examples. But that's just cubic functions in a nutshell. We'll do examples shortly. Thank you. Okay, now they're asking us to determine h prime, right? We have to determine h prime. What is h prime? So that's basically us saying h prime is, let's start with h at x. So h at x is what? X cubed minus 7x squared plus 14x minus 8. Therefore, your 8.3.1, your h prime of x will be 3x squared minus 14x plus a 14, right? That's it, plus a 14. This is h prime, right? Now they're saying determine the coordinates of the x coordinates of the turning point. Determine the x coordinates of the turning point of the English. English. So that means now you just equate this guy to 0. Let's say 8.3.2. You say h prime of x at the turning point is equal to 0. Why? Because the gradient is 0 at the turning point. So you literally have 3x squared minus 14x plus 14 equals 0. Then you solve for x here. It's either you solving for x using the quadratic thingy, or if you feel like you fit enough, you can literally use factors, but I don't think you can. I'm just looking at it. I don't want to complicate my life. I'll be like quadratic formula. Then you're done. Now they're asking us to solve this guy over here. Basically, the first thing you'll have to look for factors, right? And I'll teach you a very cool way using a calculator. So your factors will look like something like this. You literally have your f at x being equal to x minus a, x minus b, x minus c, right? Something like that. When I say a, b, c, this can be any constant, or maybe for simplicity or to avoid confusion, let me just say x minus x1, right? X minus x1, x minus x2, x minus x3, right? Yeah, so let's just use a calculator taking this equation into account. Go to your calculator, right? You click on mode, After clicking on mode, you look for an option that says table, You click on it, that's option 7. And what is the equation? The equation is saying x cubed, right? You literally have x cubed, okay? Minus 7x squared minus your 7x squared, right? You write your 7 x squared, right? 7 of x squared, right? Plus your 14x, 14 half x, minus your 8, right? You minus your 8. And then you click equal to. You just skip this part, né? Where do you want it to start? You can start it at minus 8 if you want to. Start it at minus 8 and end it maybe at 8. You can start it wherever, right? I'm just deciding 8 to 8, minus 8 to 8, and step 1, right? You see here, you look for values of x at which f at x is 0, right? Those will be your factors. So let's go now. Let's click. You literally have 1 and 2. Is there any other one? And 4, right? You have 1, 2, and 4. So that means you just have your factors. You factorized just like that. So in your first bracket, you'll have x minus 1. In your second bracket, you'll have x minus 2. In your third bracket, you'll have what? X minus 4. That's your f at x. Simple as that. You're done. This graph can be simplified into f at x equals x minus 1, x minus 2, and x minus 4, right? Where is c? C is the furthest x-intercept. So that means it's 4, it's 2, it's 1. So the coordinates of C are 4 is to 0 because C is an x-intercept of this graph. The graph H concave down at x equals k. Sorry, at x at x less than k. Calculate the value of k, right? I mean, it's simple. They are literally saying calculate the point of inflection. How do you calculate the point of inflection? By taking the second derivative. So it's h prime of x, right? How do you do that? You take the derivative of a derivative. So that means you'll derive this guy, right? And if you were to derive this guy over here, if you were to derive this guy, the derivative of this guy, it will be literally 6x minus 14, right? Because it will be 6x minus 14. And you equate this to 0, right? Because you determine what the point of inflection. Then it will be literally x is equal to 14 divided by 6. Ne? That's your value of k, right? This is the point of inflection. This is equal to k. Simple as that. They will never trick you. You just need to know these basics. Do more question papers as you possibly can. If you want to get 100, just do more question papers as you possibly can. I believe in you. 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 Bye.